Hello everyone, my name is Junluo. I am a PhD student at the University of Pittsburgh. Today I would like to talk about our work, PGFed, Personalize Each Client's Global Objective for Federated Learning. This is a joint work with our collaborators from University of Central Florida, Matthias and Dr. Chen, and my advisor, Dr. Wu. Federated learning aims to train a model over a group of clients with heterogeneous and privacy-sensitive data. Conventional federated learning trains a single global model for all clients, whereas the focus of this work, personalized federated learning, allows different models for different clients, which mitigate the data heterogeneity issue by design. In existing PFL algorithms, the way in which the collaborative knowledge transfers from the server to the clients is implicit, which means they don't directly engage with non-local empirical risks for training the personalized models. An example of explicit collaborative knowledge transfer is the global FL's objective, where we directly sum up the local empirical risks. Why do we care about the explicitness, especially for personalized model update? The intuition is that we'd like to facilitate the generalizability of personalized models directly by penalizing its performance over other clients' empirical risks, like the F2 of theta 1 and F3 of theta 1 in the following figure. We also conducted a toy experiment and observed that within only a few steps, a simple design of explicit objective, where the local objective is its local risk plus an average of non-local risk, can outperform an implicit objective. Now, why don't all PFL algorithms use explicit design? This is because its communication cost will be increased to O of n squared. Also, setting proper values for the coefficients of non-local risks is not trivial. So we proposed an explicit PFL algorithm, PGFed, with an estimate of non-local risk to reduce the communication overhead and pairwise adaptive coefficient, which is learnable during the training. We estimate the non-local risks by a first-order approximation. Plug this in the local objective of client I, and we have the following equations. What is left is to calculate the gradients with respect to the model weights theta I and the adaptive coefficients alphas. The gradient with respect to theta I is shown in this equation. The second term, g tilde n, can be computed on the server with the clients uploading the adaptive coefficients and the local gradients. The gradient with respect to alpha is shown here. The first term, g alpha 1, is a scalar, and the second term, g alpha 2, takes O of n squared communication cost to compute its exact value. So we compute g bar n, the average of gradients on the server, for computing its estimate. To accommodate the client selection, the scope of g tilde and g bar are slightly changed for each training round t. We also proposed a momentum update, PGFed mode, to keep the previous round's info, which would be lost due to client selection. The algorithm is detailed on the right. We conducted extensive experiments on 4 datasets under different federated settings. The table below shows the mean local test accuracy on CFAR 10 and CFAR 100. Here, PGFed and PGFed mode boost the accuracy by up to around 15%. We also tested the convergence speed by recording the number of rounds it takes to reach 70% accuracy on CFAR 10, and found that PGFed and PGFed mode have an average of 3.7 speed up over top PFL algorithms, with the highest individual gain. In addition, we fine-tuned the resulting side product, the global model from top PFL algorithms, on 20 new clients. The results showed that the global model of PGFed and PGFed mode have highest generalizability. More details on the convergence behavior, the adaptive coefficients and their relationship with local training set size, and other experiments can be found in our full paper. Finally, I would like to thank all of our funding agencies and our collaborators. For more details, please scan the QR code. Thank you.